I'll continue from last time, and this time I'm going to focus a bit more on the Virasoro algebra, which is an important issue of the edge, and toy models and their connection to conformal field theory. So last time I was basically telling you that for a generic theory, you shouldn't impose rotational invariance on the problem, but the most useful toy models of the system are the ones which are derived from conformal block states, and they have a very useful rotational symmetry because they're defined by essentially a metric. So the only issue is that one needs to extract what one can from these models and put it into a more general form and reject anything which is not which is specific to the properties. I'm not sure I showed this one last time, so actually it's kind of useful to see what one can actually see in doing exact diagonalization studies of the projected models. And actually these are the exact diagonalizations of the toy models. Among other things, we see that I guess I don't have a pointer, right? Does it work? It doesn't work. Yeah. Okay. So we see that there is the striking thing is that there is a unique ground state at a quantum number one can identify as momentum zero, an inversion symmetric quantum number. And if we do it on the torus, which these calculations are done on, we see that there is a topologically degenerate manifold of states because of the genus of the system. And by actually varying the aspect ratio, of course, if I take a periodic boundary condition like a torus, and there's a grid of allowed points in momentum space, but by just changing the aspect ratio and the angle between the periodically repeated vectors on the torus, we can actually scan out the spectrum. And in fact, since the actual Hamiltonian has a rotational invariance which is just broken by the boundary conditions, you can actually see that if I plot everything as a function of the length of the momentum vector, it fits on beautiful curves. And one sees from this, actually an interesting point here is for the first one of these pictures is for the Laughlin state at 1/3. And the second picture is for the Moore-Reed state at 1/2, which is really, as I pointed out, two particles in 4 orbitals, so 2/4. And because it's 2/4 rather than 1/2, you have to adapt the Brillouin zone, which comes out from the discreteness of the allowed translations, to only consider double the primitive allowed translation, which means you map a Brillouin zone from a full Brillouin zone to divide it into 4 quarters and map them all onto the same point, and then you get a nice rotationally invariant spectrum in the remapped in the quarter zone, which is an indication of this special case where the two numbers P and Q, the number of electrons and the number of fluxes in the composite boson have a common factor of 2. Okay. And other things one can see in this picture is that the collective mode at long wavelengths has disappeared up into the continuum of 2 quasi-particle and 2 quasi-hole pairs. And I used to think that was, you couldn't do anything about that. But it now appears that by suitably choosing the interaction potential, who's it in Orsay, yeah, anyway, it's been found that you can actually you can manipulate it to push the zero momentum limit of the collective mode, which has been called the graviton, which is really the long wavelength quadrupole fluctuation, down below the bottom of the continuum, which is a very interesting feature. The guy I'll say.
Was it Andre's friend Nicola? The guy who was he at Princeton for a couple of years?
No, I mean.
Then it's not Nicola.
Nicola might have been his student, I'm not sure, yeah. My brain is going, okay. Senior moment. What? No, French guy. You don't know him. It does all the numerical calculations. Okay, sorry. And in the other case, you actually see for the more read case, the quasi-particles being non-abelian, being Majorana zero mode, so they can come together either as a fermionic or a bosonic case. So when they're far apart at large momentum, the picture is just of quasi-particles. The lowest excitation is 2 of them, and as you bring them together, they cross over. There's this duality between particle-like behavior at large distances compared to the magnetic length, which transforms into wave-like behavior, collective mode-like behavior at small momentum. So the momentum now becomes h bar over the length, over the magnetic length. And you can actually see an interesting feature of the bosonic analog of the fermionic analog of the roton, which is the analog of a BCS quasi-particle in some sense, because if I were to play with the interaction in this model and it went to the composite Fermi liquid state, this point here the minimum of the fermionic spectrum is basically at what you'd call KF, the radius of the Fermi surface for the composite fermion liquid. So that would come down and go soft, and you would go into the composite Fermi liquid. So essentially, this brings up the analogy with like BCS in the composite Fermi picture. Yeah.
Can I ask one question? So this 2/4, what does that mean? Suppose that I have, an U equals 5 state, and I, whatever, I'm diagonalizing on some small lattice, and I have like an odd number of magnetic flux unit cells there. Does that mean it can't access the?
Well, one half is not possible because a composite object of 1 electron in two fluxes is a fermion, right? But that's not always the case. I mean, there are there's also cases where you get doubling like this, where the half composite object is a boson. It doesn't always have to be a fermion. I think if you take Reed-Rezai level 4, the Reed-Rezai level evens have this property. And so Reed-Rezai level 2 is more Reed. Reed-Rezai level 4 is a composite of four particles.
Those are all bosonic, essentially.
But half of that is also a boson. So it doesn't mean that the half object, if the half object is a fermion, it can't be the boson. But you can tell which is which by just looking at the grounds, looking where you find the ground state. As I just kind of pointed out, the doubled ones, they occur. There are 4 in this geometry. There are 4 inversion symmetric points, right? There's one at k equals 0, and there are 3 others at pi, 0, and 0 pi, which, if you make the boundary condition, have 3-fold symmetry, all equivalent to each other. Okay, and the 0 is separate from them. So the regular case is everything's at 0. If you find there's anything at all at the other 3, first of all, you'll always find the equal amounts at the other 3. There's no because they're equivalent. And basically, the logic is you should not be able to come up with a quantum number to split your topological multiplet, because any arbitrary linear combination of states in the topological multiplet are locally indistinguishable and they're equally good. So you have to, if you find something screwed up with your spectrum, that you get the topological multiplet split over the maximal set of quantum numbers, you have to do this reduction. And this tells you that the only 2 cases are everything at k equals 0, or stuff which is occurring at 0 pi, and pi 0, which means that you have to fold it all back into you have to use the quarter zone scheme. So the only 2 possibilities are P and Q relatively prime, or P and Q having a a relative factor of 2, and nothing else is compatible with inversion symmetry, which I've claimed is the fundamental symmetry of quantum Hall, gapped quantum Hall systems. Okay, so it's kind of interesting kind of spectrum. The thing I wanted to point out was that there's a kind of it's tempting to think that the bosonic roton will eventually go to an energy given by the zero momentum limit of Gervin-McDonald-Platzman. It's kind of tempting to imagine that the fermionic one is extrapolating to the same point, which would indicate some kind of supersymmetry. But no one, while we have a kind of good analytic picture at long wavelength from the Gervin-McDonald-Platzman calculation, we don't have an equivalent kind of Borg-Golubov quasi-particle version of Gervin-McDonald-Platzman to give us any handle so far, to give us any handle on the long wavelength behavior of the fermionic mode, which would be a kind of, if someone could find that, that would be a rather interesting feature. I mean, in some sense, the Borg-Golubov quasi-particle is somehow the natural model for that, for the fermionic thing, because you've taken if you take two Majorana zero modes which are the same and join them up, fuse them, you get a boson. But if you take two different Majorana zero modes and fuse them, you get a fermion. And of course, one is a quasi-particle, the other is a quasi-hole, so they're different. Okay, so anyway, so let's go back, review the basic picture of the fractional quantum Hall state. Elementary unit composite boson carrying charge, some number of electrons, p, covering an area of q flux quanta, q single particle flux quanta, single electron flux quanta. Then there's this emergent U1 Chern-Simons gauge field with k equals p times q, which is the Berry phase as the kind of empty bubble gets moved around in the background fluid. And when the background fluid has the right filling factor, the Berry phase cancels the Bohr-Majorov phase, and it also cancels the fermion parity of any of the particles inside the bubble. So it becomes a neutral boson. It moves like a neutral boson, and it can condense, but it has a gap because of the Chern-Simons gauge field. And the basic point is what gives this stability. That first of all, the boson has inversion symmetry, and it's got a stable shape and a stable electric quadrupole moment with a kind of shape rigidity, which is what gaps the system. So it's the stability of the shape, the fact it minimizes energy with its definite shape that gaps the system, and it's somewhat analogous to a easy axis ferromagnet with a Zeeman term, right? So where the Zeeman term makes the energy lowest when the magnetization is pointing along that direction, and it can fluctuate about that direction, but without so it's the energy that's minimized by choosing the right quadrupole moment. Okay. What's the origin of this stability? There's a nice analogy with a quantum solid like helium-4. So an empty unit cell in a solid you can think of as a correlation hole, right? And the repulsive interaction which stabilizes the solid means that there's a kind of attractive potential which has a minimum at the center of the correlation hole, the empty unit cell. And the geometry of the whole thing is defined by the shape of the unit cell. And the solid is stable provided the repulsive interaction with the other particles makes the potential of the empty site deep enough to actually bind an atom, right? So basically, you can think of the solid as forming a composite thing where a vacancy in the solid binds the particle that fits in it, and then that's a stable thing. And of course, helium solids under low pressure will melt because the 0-point fluctuations are too big, and the solid is too squishy and soft that the potential well becomes not big enough to bind the atom in it, and therefore the whole solid melts. Okay, so that's the similar story here, and as the flux attachment really is the physical nature of flux attachment is the creation of a correlation hole, and the minimum energy of that, the energy minimizing shape defines an emergent geometry, and we need the And the other thing is that the essential interaction is that the electron or the group of electrons that occupy that correlation hole, there's a kind of Hubbard-like interaction in the sense that the energy cost of they keep any other particles out of that hole, right? So they don't want, they like that occupation factor, and they don't like any, and it costs you something like a Hubbard U to put something else in, and so they exclude the other particles and keep this little region to themselves. And I think I just showed these pictures again. So in that sense, the Laughlin state, well, you've got this correlation hole. The energy levels, because there's a potential inside it, the central energy, there are 3 orbitals inside it, and you can arrange them radially. And the lowest energy one is clearly the one at the center. Okay, and we'll come back to that when I discuss the Gaffnian. And the other thing is we see that the distribution of the electrons inside the thing is not uniform. So to calculate its quadrupole moment, remember, this is not a traceless quadrupole moment. Okay. This is variance. We just the central orbital is occupied. The next 2 are empty. But if it was uniform, there'd be 1/3 of an electron in each orbital, and then we can calculate the quadrupole moment, which part of which is a quantized spin value when you have rotational symmetry. And we find from this that the guiding center spin of the Laughlin state is -1. We count the spin. It's a half, because we include the 0-point term in the spin. It's a dagger a plus a dagger. It's m plus a half. The central orbital has spin a half. Of guiding center spin a half. The second one has guiding center spin 3 halves, and you go outwards, it's 5 halves. The Landau orbit spin is in the opposite sense, and its lowest Landau level would be -1/2. Second Landau level would be -3 halves. And so when you add the guiding center spin to the Landau orbit spin, you get an integer number, but individually they're half integers. Okay. And okay, so, and there's the 2/5 state, etc. And one can sort of identify the levels inside the droplet, roughly speaking, with Jane's idea of pseudo Landau levels, right? Jane's picture of the 2/5 state in composite Fermion language would be that you have 2 Landau levels which are occupied, right? Well, here each 2/5 droplet has the central 2 levels occupied, and you can then identify the lowest level with Jane's lowest pseudo Landau level, and the second level as Jane's second Landau level. And so you'll naturally occupy them, in this case in the Pauli principle, like when you put lower central one, next one, right here.
These right now you're sort of describing these as spins, like angular momenta with rotation and variance.
Yeah.
But last time you said, well, really we should think about this quadrupole moment.
Yeah.
And so it's the idea that quadrupole moment, even if we broke rotation and variance, this quantity that you're calling S is
okay.
The same?
What actually happens is the spin is no longer quantized.
Right.
It's actually, because the actual algebra is SL2R, which is a non-compact group, and the representation can change, but the parity is conserved. So -1 to the 2s or something. So the parity, so these states are, in fact, this 2/5 state is an odd parity state. Okay. I think you have to take, yeah, you can count them. You can count them from the center outwards, and I guess you have to take the spin plus 1 divided by 2, and whether that's even or odd is actually a parity. So the parity is a good concept that remains. So we'll see that the Gaffnian involves states with 2 different parities.
And what happens to Q in that case? Because
Q in this case is proportional to Euclidean metric.
And then if I started with this, this some value of S, right? And I break rotation invariance. Is it just Q could
Well,
be
actually, you
or-
sort of have to consider S and L squared multiplying GAB, right? So the statement would actually be the determinant of Q
okay.
took some quantized value, some value which was in terms of L squared, right? It's not exactly a pure number, right?
Okay.
It's actually, yeah, when it's properly written down, it's got dimensions of charge. Oh, it's dimensions of charge times area, because the density is a pure charge, which is a much nicer thing to deal with. Okay, so and that was the picture of how electron transport happens in a doped Laughlin loop. So the simple message is that the quasi-particles and the quasi-holes of a fluid are just kind of composite bosons of a different of either a parent or daughter fluid, right? And okay, like, so in some sense it's like doping a crystal. Some of the unit cells have a different charge for the others because that's where the extra electron went, but then it can hop around. Okay, and that was just a picture that shows you that you have a consistency that you stick an electron into the 1/3 composite boson and make a 2/3 object, but that's unstable again, splitting into 3 2/5 objects, each of which carry 1/3 of the extra charge. And if I started in the 2/5 state and remove a charge, then I've made one to do a quasi-hole of the 2/5 state. I've now created one. I've made a defect composite boson with only one particle rather than two in it, but that can recombine with two other 2/5 things to form five 1/3. So it's a kind of symmetric kind of picture on either side of this lake to mountain or whatever transition, where you go between a sea of 1/3 with a few 2/5 floating around it to a sea of 2/5 with a few residual 1/3. Okay, so the boundary of the incompressible region has independent fluctuations of both boundary charge and boundary electric dipole densities, right? And in particular, that's because the discontinuity of the bulk 2D electric quadrupole at the edge produces a edge 1D dipole density, right? And both of those two quantities have dimensions of charge, right? Because 2D dipole density, quadrupole density is dimension charge, and 1D dipole density is dimension charge. So the dipole density on the edge is just the one of the components of the quadrupole is dot producted with the normal vector. Okay, so there we have our picture of the thing. So filled in the fluid, which before was sort of just a yellow blank thing, is actually built up of these little units. And actually, this tells you that there's actually a natural length scale along the edge, right? An intrinsic length scale, which is essentially the overlap of an element of the edge with a composite boson. So we can actually, so it's a bit like counting things in unit cells. We have a natural, and this presumably will play a role in the issue of how I actually parameterize the edge, right? Well, notice I've got this parameter S. Now, naively, I would just take the edge length parameter would be determined by the Euclidean metric of the coordinate system, right? That's what I'd naturally do in a geometric picture, right? But actually, as I said, the Euclidean metric of the empty space coordinate system, the Cartesian coordinates I'm using, shouldn't enter into the physics of this at all. So it's actually going to be the natural length scale along the edge will be counting distances in units of the bosons.
Sorry, I just a question. So in your last lecture, you argued that the confining potential for the quantum Hall liquid would actually deform the
So the shape at the edge is not That's not necessarily going to be the shape of the bulk, right? It'll be whatever it actually is at the edge, right?
Okay, so that you would
So-
think. Okay.
So I guess you could think of that as a kind of, if you're using these to form some kind of natural coordinate system, then I guess you'd introduce some kind of curvilinear structure, which may get back to the.
Okay, so it's my question.
Yeah.
If that performs, would that also have an effect on what you call this length scale? The center?
Yes, it will. The length scale will be whatever the actual edge value of the thing, and so the value of the dipole moment at the edge depends on the value of Q at the edge. You've integrated it through the thing, and you basically if Q is spatially varying, there's a effective dipole density or polarization of a one derivative of Q, and then there's an effective charge density of the double derivative of Q, right? So when you integrate it, when you integrate the double derivative of Q, it doesn't contribute anything to the edge charge, but the single derivative integrates and you does contribute to the edge dipole. So there are these two fields really, which have anomalies, right? There are two anomalies at the edge. There's the edge current anomaly, which is a kind of sort of U1 version of a Kac-Moody algebra. And with the correct units put in, its anomaly is just the quantum Hall conductance. And the second anomaly is the momentum anomaly. But momentum is dipole moment gets converted to momentum. So dipole moment normal to the edge gets converted by the Faraday tensor to momentum along the edge, right? The fundamental relation is, because I don't have it written on the slide, was I guess pi A is FAB PB, right? So remember in electromagnetism, the momentum pi A, if you have in a usual way treatment, pi A would be epsilon ABC, I guess dB BC, right? But dA equals epsilon 0 epsilon AB. I mean, this was the subject of the Abraham Minkowski controversy about what the correct momentum in electromagnetism was, right? It was a long-standing battle between all the big shots of physics in the 20s and 30s. The basic being that was it equal to the other one is JAU, I guess, is epsilon ABC EB HC, right? So of course, the energy current is E cross H and the momentum density is B cross D, right? But if you don't, but since people love these Gaussian units where everything's got the same value and didn't worry about the positions too much of the spatial indices, the argument was it this guy divided by C squared, or was it this guy, right? And the people who supported relativity said they love this Lorentzian variant-like formula, E cross H over C squared, while the people who liked condensed matter or quantum mechanics, right, basically wanted the momentum to be H bar K, right? And of course, the answer is, both are right in their own way, but the correct answer is this guy. That's the momentum carried by a photon, which is really a polariton when it moves through polarizable matter. And this part is the part you could, if you want to divide it up into electromagnetic and mechanical momentum, that part's the electromagnetic, but the sum of the electromagnetic and the mechanical one is the correct momentum, which is this. And the way you essentially tested it was shining a laser beam on a liquid surface and, seeing that it gets, since K gets smaller, the wave number gets smaller, when you go inside the especially if there's some momentum lost and it causes the laser beam. The laser beam causes a surface to kind of bow out until the surface tension kind of balances the loss of momentum you need to reduce h bar k. Anyway, so basically take P. So you put it's better to call this the Faraday tensor rather than but basically throwing this part away, the P part, the polarization part, it's going to do that. So that's the basic fundamental relation between. So basically the electric polarization normal to the edge rotates with the Faraday tensor by 90 degrees and it lowers its index and it turns into a momentum. So the 2 degrees of excitation of the system are the fluctuations of the charge, which is actually the fluctuations of the shape of the surface, the boundary of the surface. Little ripples of that because the charge density, according to Chern-Simons, is 0 outside and 1 in. So the little j is the shape of the surface, and pi, the Virasoro algebra, is referring to the dipole fluctuations of the surface. And the basic point is that we kind of believe that in general the Hilbert space of a edge of a quantum Hall system is a direct sum of irreducible representations of the Virasoro algebra. So I've actually put a little in my commutation relations of the momentum densities. I put a species label J on them. So the momenta of different species commute with each other, and each species has its own value of the Virasoro anomaly. And the total Virasoro anomaly is the sum of the individual Virasoro anomalies of each species. And some species can be positive and some species can be negative, because this is a reworking of the Virasoro algebra to throw away this idea that it all annihilates in one direction, which is kind of more energy centered, which people use in conformal field theory and string theory. We're throwing away all the Hamiltonian aspects of it and keeping only the spatial part. So it should be viewed as a chiral algebra with C as a signed value, right? If C is positive, you annihilate one way, and if C is negative, you annihilate in the other direction. Okay, so in this case, it's a signed anomaly, and the momentum density is really also the generator of spatial diffeomorphism of the field on the boundary. And to my mind, the occurrence in the quantum Hall effect is actually a second independent occurrence in a physical context of the Virasoro algebra, not directly distinct from its application in critical phenomena and conformal field theory. And so one question that arises, is the anomaly C purely an edge property, or is it a bulk property too? And the issue in that is that the bulk part, which invokes C, is basically we can think of all these the bulk topological theory as a U1 level K times some neutral topological TQFT. I'm not quite sure about the issues of modding of cosetting and things, but the basic issue then is that the bulk TQFT only, its kind of basic defining relations only don't depend on C directly, they depend on exponential of 2 pi I C over 8 or something. So the actual TQFT doesn't actually seem to know about C, it just knows about essentially a non-integer part of C when it's put in the right units. I guess if I change the 1/12 to, I could redefine the Virasoro algebra to not use 1/12 in the anomaly, right? Wherever it's gone. And then it would be with a redefining of that algebra, it would be the non-integer, the TQFT would only depend on the non-integer part of the fractional part of C, but not its full part. Okay, so the velocity spectrum on the edge would come from kind of operators with the Hamiltonian would involve Virasoro weight h equals 2 things like the momentum. And so of course, the leading term at the edge would be for every independent copy of the Virasoro algebra, we'd have a diagonal term, which we're with a velocity in it, which could be spatially varying along the edge, where the velocity times the anomaly has to be positive, otherwise it would be unstable, right? And then the edge would have the weight 2 couplings one can add at the edge. Well, in the multi-component abelian theory with this K matrix, the Z and when and I guess people wrote down. Then you have a load of current. Then the other weight 2 operators you could have are currents, I guess, in the same direction, and then you will mix them up, and you can just rediagonalize that, and you can get a set of modes traveling at different velocities, different speeds, right? So of course the number of right moving and the total value of C is invariant, right? It can't change, so it tells you this is a predominant right or left mode, and that's why it ends up giving you relating things to the whole thermal conductance. When you heat it up, you've got more modes moving one way than the other way, and you get the thing. And it's kind of interesting that my colleague Laughlin recently looked at so you can of course write down just a load of couplings of weight 1 current operators, right? And if those currents are U1 currents, it's just harmonic oscillators, so you just get a set of velocities. And if you have, but you could also have CFTs which have Majorana primary fields, right? In which case you can also make these actually marginally relevant terms or something with so they're marginal but relevant because they change the spectrum, right? So you could take four different Majoranas, and it turns out if you've got 4, you can still turn it into something that looks is integrable, where you get a set of velocities. But if you've got more than I'm not sure if you actually make these velocities different. Like what Laughlin looked at was the case where he took the H0 to have a universal velocity, like a Lorentz velocity, and switched on the couplings, and he found that up to 6 Majorana species, you could diagonalize it and get three velocity fields. But above that, it's not integrable, and you just get, all you do is get the spectrum. You can work out easily, there's out from the Hamiltonian, there's a maximum possible velocity and a minimum possible velocity, and then you fill in in a non-integrable way all the states in between, but but they repel each other. You see a crossover from what is it, unitary to you see the Wigner-Dyson ensemble show up, but after you've got, if you choose all the velocities the same, once you've got more than 6, the spectrum is bounded below and above by a maximum velocity and a minimum velocity, but you get Wigner-Dyson type propulsion of the energy level, so it's non-integrable.
So are you using that for a specific model with Majoranas on the edge, or in general?
In general.
If I took many
layers of quantum, actually you can do it by counting how many. You can count how many. This gamma ijkl has to be totally anti-symmetric, right? You could do something by counting the number of independent coefficients and something like that, and for small enough number of Majoranas, it's small enough that you can find it integrable, but it's generically non-integrable. You can always find if there are 5 of them, for example, you can find you can always write this. You can block this into something like H0 with currents, except you now a rediagonalization among them, right? But it breaks down at 6. Kind of interesting point. So it's so he was interested in SYK type versions of this thing, right? And found that
Are there there's still well-defined kind of mobile quasi-particles, but the velocities have this.
The spectrum, but you can't split the spectrum up into, you can't assign like a charge, right? I mean, in this case, there's you could with this picture I showed here, which would get out of something like the U1 currents, you found the basis, and there's 3 kinds of phonons, right? And they don't, it's diagonal, it's still harmonic and things, right? Well, it doesn't work for that. Interesting. So if you have representations which actually don't have any currents or Majorana primaries in it, it seems like there's no way you can construct any kind of coupling between them and the others, which is going to be marginal, right? I mean, if there's a couplings which are relevant, they just gap out and they're gone, right? So they're not present in it anyway. So the issue about different velocities is to find marginal couplings, but if like Z3, for example, there's nothing there's no primaries with kind of integer or half integer weight floating around. So it looks like those things can't, a Z3 term, which is the magic one that people want for universal quantum computing, right? The Fibonacci NEOs would be like couldn't couple to anything else, so it would be kind of like a scar. So if you had a Z3 floating around, the rest of it could possibly become, could get all non-universal and Wigner-Dyson and things, but the Z3 part couldn't couple to anything else. So people talked about scars, so it's kind of possibly interesting. Okay, so actually I don't have is there a clock here I can see? No. Okay, so yeah, so 5 minutes, I should move right through to the stuff. I want to just talk about, let's just explaining why the Laughlin state works or something like that. Basically, to think about how the droplet forms the interaction picture. The basic problem we're dealing with is written down here, right? So the fundamental quantum Hall problem after projection into a Landau level is just some Hamiltonian, and you can see the only symmetries of that Hamiltonian are R goes to R plus constant and R goes to minus R, right? Without me saying anything else about it. They're the ones that preserve the algebra and they preserve the Hamiltonian. And we can see that if the particles are identical, you've automatically got inversion symmetry just under interchange of the particles. So even if the underlying problem did break inversion symmetry, for example, if the Landau orbit form factor had some odd Q terms in it, it still won't have a linear in Q because we've removed the linear Q term in the form factor by insisting it has no dipole moment, but it could be odd. But it occurs in the form f of Q, f of minus Q in the projected Hamiltonian. So you see that the Hamiltonian, even if underlying physics has some has broken in some small way rotational symmetry, 180-degree rotational symmetry, the projected Hamiltonian has it, and that's the basic fundamental one. So if you solve the two-body problem, the basic thing is that so I probably had it somewhere here, right? The smoothing, the projection into the Landau level, of course, removes the singularity at the center of the Coulomb interaction. So you had a smoothed over Coulomb interaction, which is like an upside down potential. And if you solve the two-body problem, it maps into a one-body problem in an upside down potential. So the highest state, of course, is the closest together state, and the Laughlin state very cleverly avoids putting any two particles in the highest possible state of a pair of particles. So in a sense, the shape of this upside down potential will predominantly determine the shape of the flux attachment scheme. Okay. Other points in this thing, if the liquid is actually flowing, you displace the charge center, gets displaced a bit from the inversion center of the flux. It's a kind of linear response. And so actually, there was a lot of discussion in terms of the Ginzburg-Landau type model, why the effective mass of the the composite particle was not the electron mass, right? And there was a whole discussion. It's really that the effective mass is what's the susceptibility tensor. So there's some susceptibility which actually can vary between different Landau levels if it's not rotationally invariant. And so the electric susceptibility tensor just maps back and tells you what the extra energy associated with the flow velocity of the thing is. Okay, let's move forward on this. Okay, and basic point is that, yeah, this is just saying that Laughlin actually, in some sense, you shouldn't talk about a wave function once you project it, at least anyway. You should talk about a Heisenberg state, and Laughlin state can be much better represented as a Heisenberg type operator acting on a vacuum. I guess it's because once you've projected into a Landau level, you have a non-orthogonal, the projected states are not orthogonal to each other. And actually the truce between Schrödinger and Heisenberg, which says they're describing the same physics, actually relies on the fact that there's a local basis, which is where different positions are orthogonal to each other. So once you remove that ingredient, you find that Schrödinger slips below Heisenberg in the scale of generality. So Heisenberg is still okay, but Schrödinger misses. And in fact, people are now using this for, I guess, all the twisted bilayer graphene projections in a flat band. So if you project, if you've got more than one orbital in a cell and you project onto those orbitals, you've got an overcomplete basis. Okay, let's move forward on this. Well, yeah, so Laughlin state is an interesting state where you have a Hamiltonian which has a kernel of zero energy states. Okay, and this is an example of looking at the Laughlin state for, I think, 6 particles on the plane. And you see that this is 6 particles on an infinite plane. So there's a whole spectrum of kernel states, and the most close together one is the Laughlin. And the relation to conformal field theory is as follows. There is actually no relation to conformal field theory with these states, excited states. It's the kernel, the toy model Hamiltonians like Laughlin. Their kernel is described by, can be counted using Jack polynomials. Come back. And the Jack polynomials is a family of polynomials that when they have a negative rational Jack parameter, which I'll come to, they actually they map into a Virasoro. They have a Virasoro algebra floating around inside it. Okay, and so it's only the null state of the toy models which actually maps into, has a one-to-one mapping to conformal field theory. And if I were to put this on a disk or something like that with little potential, the edge states would all grow out of the kernel states, right? So the spectrum of the low-lying states at the edge, which give you a kind of one-to-one correspondence with the character table of the conformal field theory, is actually just counting the kernel states for a given particle number with respect to the angular momentum, and that really becomes a Virasoro weight relative to, in this case, you'd count 30 as 0 in Virasoro, okay? So the Virasoro weight would be the axis that way measured relative to the maximum density state. Okay, so it's kind of an interesting mathematical problem to try and get a rigorous bound, because there's strong analogies with AKLT states here, where people manage to get a rigorous bound to the gap. But there's an interesting point here. These states, this system has a kernel, and it's got the kernel states and non-kernel states. You might wave your hands around and say it's obviously gapped, right? And of course it really is gapped. And if you actually look at how the gap behaves as a function of size, it goes down a little bit initially, but it basically saturates and only changes by exponentially small amounts as I go to larger and larger systems. So empirically, it makes sense that the fact it's got a kernel means there's a gap between the kernel and non-kernel states. But I mean, a true mathematician would point his finger and say, okay, you haven't proved anything. And he would be right, because this other state I'll show you, the non-unitary state, actually goes to 0 if you make the system bigger enough, because it's not a gap system. Okay, so let me just move on to what I want to. So it's a kind of interesting challenge, and it's people have started to do it, but they haven't actually got it out for the Laughlin and conformal block states yet. Okay, entanglement spectrum. So the entanglement spectrum you see for the toy model states is essentially in one-to-one correspondence with a slightly truncated version of the Virasoro thing. If I were to make them bigger and bigger, I would, so the low-lying part of the spectrum it is one-to-one with the character count, but I can't. It's like I've put a bottom. The finite size puts like a bottom to my Dirac C or Fermi C, right? So once I get to momentum, which I could excite by digging something up from below the lowest possible state, I start to lose state. So it's the character table is complete for a bit, and then it starts to lose states. But as I make it bigger and bigger, the place where you start to lose characters goes away. Okay, and what you see if I switch on the interaction between if I switch on a modified interaction, which is generic, I start to pull down. There are all these levels which would be up at infinity, having negative 0 weight, and the spectrum is the pseudo energy in the spectrum is the logarithm of the weight, right? So as the weight comes, so for the real system, all these extra levels come down from infinity as I switch on the interaction, and you can see that. So the point where the vacuum is, in this case, I've drawn it so everything is going one way. You can see I've got anti-chiral states above the gap, and I mean the other degrees of freedom and the thing. And so we actually lose conformal invariance. It's only the pure spectrum of the toy model that has a direct conformal invariance thing. As of course, as I get, if I make it a very small perturbation, I can still kind of follow this gap for quite a long way, but then it kind of coalesces, and I can only see the character table of the conformal field theory in the low-lying part. Okay. Other thing is you can actually measure out of this entanglement spectrum a bulk value of C. So the issue about C only being defined modulo 8 says that you can always, well, you can wave your hands around and say, I can always add some edge reconstruction that adds a C equals 8 theory, which has some no internal content whatsoever. But actually, what you actually find kind of interestingly, when you've divided the thing up, if I calculate C for free fermions, right, I have to calculate some Q1 minus Q2 squared, where they add up to 0, something below the Fermi, below. I have to sum all excitations which for Q, which take me from the below to above the Fermi surface, and weight it by Q squared. That's a simple calculation, and it gets multiplied by the step function at the Fermi surface, right? So actually, if you follow the standard calculation of C for free fermions, but you modify it to say that the occupation factor doesn't go between 0 and 1, it goes between nu and 1, you will actually find C equals nu for free fermions, where nu is the jump at the Fermi surface. And indeed, if you divide the system up into, take out the Landau orbit degrees of freedom and focus only on the guiding center degrees of freedom, which are so-called orbital entanglement spectrum, you actually find you don't measure C, but you measure C minus nu, which I call C tilde. And C tilde, which is the, so nu, of course, the Chern would be the Chern number for integer Hall effect. So value C equals nu is the natural value we have for free fermions, right? So it turns out the free fermion, or at least the Landau orbit, the step function at the Fermi surface part, edge function, the step in the occupation factor, the edge gives you C equals nu contribution. And the C tilde, which is C minus nu, is actually odd under particle Hall transformation. Okay. So if you actually calculate now the, what you have to do is you're going to calculate the orbital entanglement. You're already calculating the Virasoro level, which is the momentum times the length of the boundary divided by 2 pi. And the momentum of the boundary is, there's a momentum per unit length, right? So this thing actually goes like the boundary length squared, the leading term. And what actually comes out of it, the leading part, if I now put the entanglement spectrum, put it on a cylinder, essentially, I interpret this as a set of energy levels at temperature 1. The ground state is down here, fictitious temperature 0, but I want to calculate how the momentum is shifted relative to the ground state at 1, temperature 1, and that's exactly what this calculates. And so the leading term gives you, which is proportional to L squared in this case, gives you the whole viscosity or the quadrupole tensor. So it's used like a metric, except it's signed, right? And then the leading term actually gives you C tilde minus C. So it shows at least a clean boundary produced by entanglement cut in the bulk tells you that C has a bulk meaning, okay, which still needs to be tracked down, okay. So anyway, you do it for Laughlin, you find that 124 C tilde minus 136. So you get numbers which are puzzling initially until you realize that there's this additional contribution. And all this Jack polynomial stuff, it relates Jack polynomials in general to W minimal models. But the last thing I wanted to say was the Gaffnian. So Laughlin state, the Jacks have a kind of generalized Pauli principle where they're characterized by rules that say things like I can't put more than 2 particles in in X boxes, right? So the bosonic Laughlin one, the simplest Jack case, is not more than 1 particle in 2 orbitals, and so you could the kernel states can be indexed by patterns of this form. But the kernel states are derived from these original patterns plus a squeezing, which depends on the chirality. So anti-Laughlin would squeeze one way and Laughlin would squeeze the other way. So the Moreed is not more than 2 particles. For the fermion case, it would be not more than 2 particles in 4 boxes. And for the boson case, the Gaffnian is not more than 2 particles in 3 boxes. And the fermionic version is a 2/5 state, which is not more than 2 particles in 5 boxes. Okay, and this is there's a perfectly good model for that, which it takes the lowest order pseudopotential for 3 particles, and then the second one. Those are both unique things. So there's a toy model called the Gaffnian, which describes for fermions a 2/5 state. And it looks like a Laughlin Hamiltonian, but the associated, when you look up the associated conformal field theory, it's non-unitary. The Virasoro algebra is non-unitary. And it turns out to be gapless, right? Let me just show the pictures, right? It doesn't really matter. So what's the basic thing? We actually have two basic patterns. For fermions, we have 2 basic patterns where you put 2 particles in 5 orbitals. And on the torus, there are 2 kind of repeated groups of 5, either 1, 0, 1, 0, 0, or 1, 1, 0, 0, 0. And if I turn this thing on its side, this is actually like, or you can think of this as filling the composite boson up from the center. So these 2 states actually have opposite parity, because the one to the left would interpreted as a composite boson. The one to the left has the leftist one is even parity, the second one has odd parity. So the blue region has a larger quadrupole moment, and it's got it's got a smaller quadrupole moment, and it's got 2 even parity orbitals occupied inside the droplet. And the other one has 1 even and 1 odd. So they can't mix, or if they mix, they would break inversion symmetry because they have different parities, and they have different quadrupole tensors. So there's a momentum per unit length along the boundary. This theory has a Virasoro algebra with one negative weight primary field, which is what makes it non-unitary, right? So then we should ask, what is the physical interpretation of that single non-unitary primary field? Well, it has to be the point of the field that represents the point of attachment of the domain wall between the two different states. So these two states have exactly the same edge anomalies, the same C and the same quantum Hall. So C, and there's no chiral edge modes on this dotted line. All we have on the dotted line is there's a momentum per unit length or a dipole moment per unit length because of the discontinuity in the quadrupole moment. So presumably, since this thing turns out to be gapless, that the surface tension between the two phases is either 0 or negative, right? Negative is not too bad because these things are slightly fat, so they wouldn't fill all the space inside the thing if they were negative, because their fatness means that they can't they will saturate, right? So it's actually not clear. There's the picture of the thing. So it's actually possible this is what seems to represent a critical point of some kind between two different versions of the 2/5 state, where the composite bosons differ fundamentally by having one being even parity and the other being odd parity. And so you're stuck with having a boundary between the well, if the boundary between the two is flexible and takes over the inside, it means that if this thing moves here, right, it's feeding momentum into, as this moves like a bead, it'll feed momentum into the interior or extract it if it moves in the other way. So it's telling you that the momentum conservation law at the surface has failed. And this was exactly an argument that Nick Reed made against saying that if the edge algebra was non-unitary, it had to mean that the gapless degrees of freedom leaked into the bulk. And again, the regular bulk has no low-lying dipolar excitations in it, and that's why it's incompressible. So I don't know if this toy model has got how generic this is. I mean, it's surprising that you find a critical point. You'd have thought that you only got first order transitions between different quantum Hall states, right? But of course, these are different quantum Hall states with exactly the same chiral edge anomalies. It's got this additional feature of the quadrupole moment of parity. The best guess, I guess, I'm not sure if there's any really basis to it, but I guess Joel Moore guessed that he speculates that it's probably a z=2 type of thing. It doesn't look like it should fit into a proper, 2+1 dimensional conformal field theory. And it may have z=2, but it's not clear, how much fine tuning is. This is obviously an incredibly fine tuned model. I mean, it hasn't been tuned, but
but you're saying the Gaffnian should be viewed as the critical point.
It's some kind of critical point between two different 2/5 states with different parity composite bosons. And usually you think of first order transition between the two, but for whatever reason so if I add a bit of two-body interaction, I presumably split that, and it'll either be two different 2/5 states. Now, if you actually look at the physical picture, you can see that the second one is actually more appropriate for the second Landau level, because in the lowest Landau level, I've got a very deep potential inside my empty little droplet. So obviously the first electron goes deeply into the center. The second one, of course, it wants to get away from the other electrons, but it's also being repelled by the one that's already there, right? So if the potential is deep enough, the potential wins and it goes into the lowest orbital. But in some sense, you can think of the electron that went into the central orbital as created a kind of Mexican hat feature. So actually the second electron doesn't want to go into the next closest to the middle, but the third one, right? So it makes kind of sense. Certainly as you go up into higher Landau levels, the second pattern where the potential, the Coulomb, the projected Coulomb interaction gets more smeared out and more damp at the center could work. So anyway, it's a kind of interesting case. And it's a very concrete toy model. Numerics show that it's out of the range of exact diagonalization in the sense that if you extrapolate it, it looks like the gap closes around 72 electrons or something. The gap does keep going down, while in the Laughlin state, the gap saturates pretty quickly and doesn't change after that. Anyway, there you are. If we're talking about gapless critical points between topological states, kind of interesting. I guess I've run out of time and it's lunchtime. So what have I got here? Many open states. I didn't say everything I wanted to say, but actually it's maybe a kind of artificial toy model, but it's actually quite an interesting possible example of something to do with critical behavior of some sort and topological states. Thank you.
I have one short question, because in the last slide I got thoroughly confused, most probably because I think of the right chapter as what's the root partition for my usual two-fifths.
Okay, it's not the 2/5 state partition, right? The 2/5 state is, if I actually, I guess, exactly construct according to James' construction, the 2/5 state, it doesn't have a consistent root pattern. So if I put them on the sphere or whatever, it has an edge reconstruction. So I can't remember which of the two it is. So Laughlin state or Moore-Reed state, they all have a perfect pattern. But if you actually take the 2/5 state as proposed and implement that proposal, you find the bulk region has I think it's the 101, the 10100101010, but it actually gets at the end at the two ends of it. It actually
So I should think of that as the 2/5.
So it's capped by, so it's not a perfect. So it does obey a kind of squeezing rule from a root configuration, but it's not a kind of perfect root configuration. I mean, but it's not the exact eigenstate of any model. It's a kind of invented, reasonable, but invented by fiat kind of thing. The other ones, the Jack ones, have a bona fide, and the Gaffnian too, for all it's worth, has a bona fide existence in the sense that there's a model there's a Hamiltonian to go with it, which has a kernel, right? And of course, it would be very nice to find but I'm not sure if there's anything else besides these Jack structures, right? That's exact, right, with kernels. So the Gaffnian might be the nearest thing to the 2/5 state that exists in the models with a kernel. And then it has this kind of curious feature that there are two different 2/5 states like on top of each other.
Actually, so for the long wavelength part of the limit of the GMP mode, you have this nice picture of shape fluctuations in the product. So I remember that I think you wanted to think of the fermionic mode where we did some kind of gravitational.
Yeah.
So sort of simple picture of what that mode is, the fermionic mode in the long wavelength limit.
No, I mean, we don't have anything like GMP's nice construction for that. But if you take the viewpoint that what the Moore-Reed state is showing is a kind of something that's a strong coupling limit of a BC that emerged continuously from a weak coupling limit where some gap opened and you had a BCS type thing to a strong coupling kind of P-wave pairing or something, then that would be the fermionic mode would be the Bogolubov mode, right? I mean, it goes to you just take the particles and holes in free fermions and they cross at the Fermi surface. Yeah. They cross at the Fermi surface and then then you open up a gap, and but I tried. I didn't manage to find a kind of I mean, the nice thing about the GMP construction is the single mode approximation is in fact, when you check it numerically or whatever, becomes asymptotically correct at long wave. It becomes exact at long wavelength. And what GMP didn't do, they found this nice expression. They found this thing which was quadratic, which was quartic in the wave number in Q in the wave number on the numerator. The denominator was the structure factor, very much. I think Platzman suggested that based on, rotons in helium, right? You've got h bar squared, k squared over 2m in the numerator, and then structure factor, the denominator. Here, there wasn't any kinetic energy, it got replaced by something. But it turns out the long wavelength limit of the GMP thing on the top thing, the thing that's quartic in wave number, is actually just the coefficient of that quartic tensor, fourth order tensor, is actually just the strain energy. I take the exact ground state, I apply this quadrupole field, which is the strain field, which is a generator of strains. I strain a strain is parameterized by a symmetric tensor. So I strain it and I calculate the expectation value of the grounds of the strain state in the true Hamiltonian. Of course, since the unstrained state is the perfect ground state, it goes up quadratically, and it goes up quadratically proportional to this symmetric tensor that describes the strain. So it's a kind of symmetric fourth order tensor, which is really a symmetric tensor in the first pair of indices and the second pair of indices. And that's actually that strain energy. Essentially, we've done an elastic strain, not by in a crystal, of course, we can push the edges in, right? Here we've somehow done a strain on the basic shape of the metric, but that's exactly what's at the center of that's the top line of the GMP thing, and that controls the energy. So it's actually the energy cost of deviating the quadrupole moment from its preferred thing. So it's kind of like just like a susceptibility, except now it's got it's a susceptibility tensor with pairs of indices, a bit like what Fiona was talking about. So
maybe the last question is from the chat. Let's go by John Harnett. Does the appearance of Jack polynomials mean a connection to Quadrupole most?
There is a connection. Okay, so Jack polynomials first occurred, I think. I'm not sure. It may have occurred in mathematics, but it certainly occurred in physics in Calogero. The interesting thing prior to this paper by Jimbo and co, which you can actually find if you look them up. Jimbo, Miwa, Feigin, Jimbo, Miwa, Mushkin, or something. All the work on Jack polynomials had been most work on Jack polynomials had the Jack parameter real positive, and that's what occurs in Calogero-Sutherland, because it's just a coupling constant of Calogero-Sutherland for real positive. Then there was work which extended it to complex values of the Jack parameter. It turns out, except on the negative real axis, except at rational values on the negative real axis, the Jacks in what are called monomial representation, where you choose the kind of leading term to be 1 in the polynomial, they're a complete basis for the symmetric polynomials. But along these special points with rational values from which you get P and Q out of on the negative real axis, you can't normalize that. Only a subset of Jacks can have a monomial normalization. And so you somehow throw a lot of stuff out of the Hilbert space, and they start to represent these restricted Hilbert spaces of polynomials. Like the simplest case, alpha equals -2, is Jack parameter -2 is the symmetric polynomials that vanish as two come together, i.e. the bosonic Laughlin state. So we didn't need the Jack polynomials to tell us how to write down the bosonic Laughlin states, but they do tell us a different way to write down the more Reed state, and even better, they tell us how to write down the Reed-Rezai states and things like that, for which there isn't any kind of Pfaffian type of description, right? So yeah, they're kind of remarkable, actually. And another thing about the Jacks is they're polynomials, but if these Jack rules, so the states are obtained by squeezing the root states. But if you count the states on the torus, which doesn't have there's no one way for squeezing, right? The count of states is still correctly given by applying these rules on the torus, but now there's no There's no kind of, there's no algorithm for actually finding the eigenstate, finding the states themselves, because there's no one-way squeezing, and the whole Jack thing was based on a lower triangular matrix, so you could just kind of turn the crank and you can work out all the coefficients.
I think John is asking maybe if there's a direct connection between the models, the fractional models.
I don't know. I mean, you actually can also associate fractional statistics with the Calogero models, and you can solve them. The difficulty in the 2D thing is, in 2D you need Z star if you write them as complex numbers, right? You got Z and Z star. In 1D they're on the unit circle, and Z star is 1 over Z. So actually I could do a complete polynomial kind of description of everything on the circle, because I don't need Z star. So Z star is 1 over Z, and I have Lorentz type expansions. But you can work out many properties exactly for the Calogero model. It's also got features like Laughlin. If you choose the parameter to be like integer, like 3, it's got 1/3 excitations, and they kind of fill a kind of, there's a kind of Fermi C, and you have the same pattern that, yeah, so there's definitely some connection. I know Bigman wanted to find it and he didn't. I mean, you look at it and you think there must be something there. And the fact you can actually solve some things exactly on the 1D case, and you can sort of imagine how they generalize when you kind of turn the circle into the disk, right? I mean, yeah, it's very, I mean, yeah, it's an open question.
The energetics are quite different, right?
The energetics, the Calogero model has a Hamiltonian that organizes the states, right? The normalization of the jacks depends on the geometry, right? And the jacks in that geometry or form an orthogonal basis, therefore they can be the eigenstates of a Hamiltonian. The jacks on for other geometries, like on the circle or on the disk or things, the jacks are not on they're not an orthogonal basis. They're linearly independent, but they're not orthogonal. So there's no Hamiltonian for which those jacks are an eigenstate basis, but all you need is linear independence, right? They're a complete basis because they're linearly independent, but not orthogonal. So it's not clear. So there's no kind of integrable Hamiltonian floating around as far as I can see.